we're still on the topic of Fibonacci series, okay? So remember that we begin with this difference equation, yn equals to the previous two terms. If you sum up the previous two terms, and as a difference equation, the system can receive an input. But then we are focusing on the impulse response, which means that we're interested in finding the system's response when it receives delta as its input, okay? So this is our system H, and when it receives delta, when it receives 1, a unit sample at time 0, and then nothing more. If the input is that, the output is what we're finding right now, okay? The output is what we're finding right now. So, but basically, simply by plugging, this is our input. If you just plug this into this line of your computer code, this is one line of your computer code, right? And you run it iteratively while true. You do while true, n equals to n plus 1. Okay, yeah. 写程式, yeah, right? You just run this code iteratively, 递回的去算. You find out that the output y should be equal to 1 at time 0, then still equal to 1 at time 0, but then 1, 1, 2, 3, 5. Then we expect the output to be the Fibonacci sequence, right? Yeah. So far so good. Is this clear? As a line of computer code, you don't even need to know about the transform. Just run the code. This is a result you should expect to get, right? As a line, as a little program, and so on. Okay, and every term is an integer. So it's a bit funny if this is the first time. When I first encountered this result, I find it amazing. It's amazing that even though each term is an integer, but if you talk about general expression for the nth term, if we consider general expression for the nth term, then the square root of 5 shows up, which is an irrational number. 这是无理数啊, right? So at least to myself, when I first encountered this result, I found it amazing. Okay, contemplating on the result, even though every term, and if you don't believe, let's try. Okay, so if you don't believe this expression, let's try to see if it really is true. Is h of n really? Is it really that? Is it really this big factor right here, p1 to the nth power minus? Are we really sure this is the result? Yeah. For n greater than or equal to 0, is it really the case? Right? So let's plug in a few numbers. Let's check. If n equals to 0, what do we have? When n equals to 0, right? When n equals to 0, seriously, we can check. 1 plus square root of 5, 2. Then on the left, we have h0 equals to that, and something to the 0th power, so that should be 1. Yeah. You can check a few terms. Yeah. Also this term, p2 to the 0th power. Yeah. So that's 1, that's 1. So we have h0 equal to 2 square root of 5 at the bottom, 1 minus square root of 5 minus 1 minus square root of 5. Then indeed, lucky, it's really 1. So h0 is correct. Yeah. And how about n equals to 1? h1, seriously, we can check if it equals to this. And now p1, that's now the tough part comes in, but you know what I mean. We can really check. Yeah. So let's take a look. So now we have 4. It seems like we have 4 square root of 5 at the bottom, and on top we have 1 plus square root of 5 square minus 1 minus square root of 5 squared. And what is that? What do we have? Still have 4 square root of 5 at the bottom, but on top, we have 6 plus 2 square root of 5 minus 6 minus 2 square root of 5. And lucky, again, h1 is indeed still 1. And so on and so forth, okay? So if you don't believe yourself, you can do some numerical check of sanity to see if the equality so this really is an expression for Fibonacci series, okay? For Fibonacci sequences. Okay, so that can be checked. And what's next? So next we need to mention a few things, a few conditions for the equality to hold, for us to apply, okay? So I mentioned that in general, when we have this formula, the kind of a reverse formula for geometric series. On the right, we're summing up a geometric sequence, p z minus 1, p squared, z minus 2, p third, z minus third. That's a geometric sequence, okay? For the equality hold, we want the common ratio to have an absolute value that's less than 1. 公比嘛, the common ratio right here has z inside, so the common ratio, so we need to just, for the sake of completeness, we need to talk about this, okay? So a few points for us to mention, okay? The first, what we have is to obtain an expansion of h of z as a power series of z inverse, okay? Power series of z inverse. And equation 6, so on the previous page, this is equation 6, okay? Equation 6 is here, let me just again write it. Here we have alpha 1, p1 to the nth power, plus alpha 2, p2 to the nth power, okay? That's equation 6 on the previous page. Let me double check. This should be equation 6. Equation 6 right here. So take a look. Alpha 1, p1 n squared, alpha 2, p2 n squared, okay? So that's equation 6. But from here to here, the equality hold only if both these factors have absolute value of less than 1, right? Otherwise, we cannot write this equality. Okay? We cannot go from here to here. This equality has for this equality to hold, there is a condition. Okay? There's a condition which requires that both this factor and that factor should have absolute value of less than 1. So that is to say, for this equality from there to here, for this equality to hold, we need to add a condition, okay? The condition is for P1Z inverse, that's a common ratio. Absolute value should be less than 1, and P2 here also has to be less than 1. Both of them need to hold. Both of them need to be true in order for us to proceed from this line to right here, okay? Equation 6, that's equation 6. Equation 6 holds only if both conditions are satisfied, all right? So how's it good? Yeah, is it okay? And or equivalently, or in other words, okay? In other words, we need to have, if we just move z to the right-hand side, we need to have z. The equality hold only when z is greater than p1 and when z is also has to be also greater than p2 absolute value. Okay? In other words, z has to be greater than both of them. Or we can say z has to be greater than the bigger one of the two of them, okay? Which is 1 plus square root of 5 divided by 2. Okay? In order for this line, this very line, to in order for us to go from there to here, we need to ensure that this is only true in a region where z absolute value is greater than this radius of 1 plus square root of 5 divided by 2. Okay? Yeah. So, and then again, let me mention that equation 6, then now the next point is about equation 7. Okay? In equation 7, that's the next one over here. That's equation 7. Okay? Equation 7 is just a simple definition, right? So I was saying that if we have two power series, we have two power series, and the equality hold over a region, and this is a very basic property in complex analysis. 复分析啊，复变函数论。Okay, it's a very pretty basic property that when we have two power series, they may look different, but if you say the equality hold, then every coefficient should be equal. Okay, so you can plug in n equals to 0, n equals to 1, n equals to 2. H0 should equal to this, evaluated at n equals to 0. That's what we're doing right there. Okay, okay, so that's a very basic property. We cannot have two. We will never have two different looking power series that turns out to be the same. That's basically the idea. Okay. Or same principle can be applied to a polynomial too. 多项式也是这样. All right. So you have this, when this equality hold, and we know that it holds because this is simple definition, then the logical consequence is that each coefficient hn should be equal to this expression evaluated when with n right there. Okay, they should equal everywhere. All the coefficients they should equal. Yeah. So that's a kind of a subtle point that I think we also need to mention. We are comparing the coefficients on the two sides of equation 7. And each pair should be the same, since we know the equality hold. Okay? Then what we get is now we get a general expression of h of n. Okay? So that's what's going on right here. And the next point is a terminology. Right? So we know that equation 6 holds, and that's part of our derivation, right? So this region where equation 6 holds, where we can apply equation 6, that region is called the region of convergence of this system. Okay? Of this particular system, this is a system. Of this particular system, now we can define its system function, and we interpret the equation in a causal manner. Then the region of convergence for our derivation to move on, we can define this region to be, it's called the region of convergence, where this power series converge back to the fractional expansion formulation. Okay, the region of convergence for this equality to hold. Right? It holds only over this region, which we call ROC. Okay, the region of convergence of this system, which is outside the circle. Okay, z absolute value greater than that. So let's take a look. So often you can just we can also try to make a sketch of this region of convergence. So we say that h of z equals to yz divided by az and equal to 1 minus z inverse z minus 2. Okay? Over the region over the region of Z greater than this radius. And this is a subset of the complex on the complex plane, right? So this subset, this region on the complex plane, if you will, is on the Z plane with real part horizontally and imaginary part vertically. So this is an outside the circle, okay? Outside a circle which center at the origin with a radius of this radius of 1 plus square root of 5 divided by 2, okay? Which is roughly what? Roughly 1.6 something. 1.6 something, okay? Yeah. 1.6 something, okay? Yeah. So there's a radius, a circle of exactly that radius, and our region of convergence of this system function is outside. It's outside. Okay? It's outside, and just long story short, we have shown in the previous hour that if now if we consider h of z only in the outside, in this region of convergence, which is outside this circle, then we can be sure that indeed h of z can be expanded as the sum of two power series. Yeah. Sum of two power series. Sum of two power series. We can be sure that equality holds, long story short. Okay? Starting with the system function and then focusing on this region, then we are sure that h of z can be rewritten in this expression. Right? And from there we find h of n. Okay? From there we find h of n equals to exactly that. Okay? N greater than 0 or equal to 0. Okay? So that's long story short, and this region has a name called ROC, or not Republic of China, but region of convergence. Okay. And it's a causal system, right? H of n is defined. It's all 0 before time 0. Yeah. So far, so good. But the next is a note, okay? So note that this region of convergence, for this very system we have, for this exact system, the region of convergence does not include the unit circle. Why? The unit circle is inside this bigger circle, right? This radius is 1.6 something. It's larger than the unit circle. Okay? So the unit circle is inside, but the region of convergence is outside. Okay, for this this exact example, the unit circle is smaller. It's inside. That's the unit circle we have. Yeah, 1. Okay. So now here comes the question. Remember that we said in the previous meeting, we said, what is DTFT? Is there the relation between DTFT and Z transform, right? We say that, I share with you that DTFT is what? Is Z transform evaluated on the unit circle. I said that, right? Yeah. Remember that? DTFT is Z transform evaluated on the unit circle. Okay. H of Z, DTFT. When we have the impulse response, its Fourier transform is DTFT. Okay. Is defined as h of n e to the minus j omega n, summation over all n. Okay, that's the definition of DTFT, and we say that DTFT is Z transform evaluated on the unit circle, or is it just simply Z transform on the unit circle? And that's why we write DTFT as H. Same H, but evaluated with Z equals to that. And that's on the unit circle. z equals to that, this thing here is on the unit circle with omega can go from 0 to pi all the way to 2 pi and just repeatedly. The spectrum is periodic, okay? But now here comes a kind of a dilemma, right? We say z dtft is z transform evaluated on the unit circle. But in this case, we say z transform is not defined on the unit circle because the region of convergence is outside this bigger circle. So how do we resolve this conflict? 这好像有点冲突在这边啊，有没有感觉到啊？这 what's going on, right? How do we kind of mitigate 就是缓冲啊，来调和 ？How do we resolve this conflict? Or is there really any conflict? Is there really any conflict? If the ROC now does not include the unit circle, that means what? That means the z transform of h of n cannot be evaluated on the unit circle. That's the implication. It doesn't converge, right? It's outside. It's not in the region of convergence, right? So by definition, the z transform of Fibonacci sequence does not converge on the unit circle. That's what we can conclude. Let me repeat this. Okay? The region of convergence does not include the unit circle. Therefore, now what we're talking about the z transform of h of n. That's big H of z. Okay? Equals to that. Yeah. So we are saying that this thing here does not, 不要写 limit 啊，也可以啊，就 Note that this is an infinite sum, okay? So this infinite sum does not converge at z equals to ej omega. That's an implication. So really, there is, if you think about it, there's no conflict. Okay, we have a system. We know the response is going to be Fibonacci sequence, which has a general expression like that, and we can be sure that it does not converge on the unit circle. So that means what? That means the Fourier transform of Fibonacci sequence does not exist. We have a sequence 1, 1, 2, 3, 5, 6, 8, 13, 21, and so on. This as a signal is well defined in time domain. But let me emphasize that this signal does not have a spectrum. Because if you just try to evaluate the DTFT, it does not converge. DTFT is an infinite series, and it does not converge. The DTFT of Fibonacci sequence does not exist. That's the way we should understand. There's really no conflict. We must acknowledge the fact that some signals simply do not have Fourier transform. Right? So that's an important kind of message I want to deliver today. Right? Some signals do not have Fourier transform. Some signals do not have Fourier transform. Right? So this is my conclusion. A kind of important message I want to make sure that we understand. Okay? In other words, the Fourier transform of Fibonacci sequence does not exist. Okay? So far so good? Can we agree on that? Can we try to agree on this? Right? So do you want to hear an even more tricky thing? It could be pretty misleading. This is important. Fourier transform of Fibonacci sequence really doesn't exist, but some people may argue, but take a look. This is h of z, right? And funny that if you write h of z in this expression, and you try to evaluate h of z on the unit circle, put a question mark, you can still come up with this idea. And everything looks fine. This is kind of a more tricky question. Yeah. My suggestion is that simply do not do this. Okay? Do not do this. This is misleading. This could be misleading, right? So simply do not do this. If you talk about Fibonacci sequence, we have an example where a signal does not have Fourier transform, no matter what. Okay. Do not try this. That's my short answer. Think about this. This could be pretty confusing right here. That's a potential point of confusion. 这个是可能让造成混淆的地方。Please do not do this. Okay? Yeah. All right. So now we can spend some time to talk about stability. Okay? Yeah. So now we have the Fibonacci sequence as an example of an impulse response to a difference equation. And then in this difference equation, one of the roots of A of z is outside the unit circle. So A of z have two roots. One is right here. That's 1 plus square root of 5 divided by 2. And the other one is somewhere right here. The other root is 1 minus square root of 5 divided by 2. That's the other one. One inside the unit circle, the other one outside the unit circle. Okay? And so therefore, when we take the limit of n approach infinity, when we come back to this expression and we let n go to infinity, what happens? This one diverges, right? This term diverges and this term converges. Okay? One of the two terms diverges, the other converges. Okay? But the sum diverges. So limit of h of n when n approaches infinity does not converge. Okay? There's explosion. This one will explode. 会爆炸啊 yeah. 爆掉 yeah. So therefore, we say that the system is not stable in the bounded input, bounded output sense. Bounded input, bounded output. Okay, literally, what does that mean? So here, recall that impulse response is a response to delta function, right? Delta function is bounded. Here we have an example of receiving a bounded input, and actually, as a matter of fact, the input has only one term, one sample, one non-zero sample. It's certainly bounded. The input is bounded, but the output diverges. Bounded input, unbounded output. So in that regard, the system is not stable. It receives just one tiny stimulus, a click, one sample, but then the output keeps growing. The output keeps growing, right? 1, 1, 2, 3, 5, 8. It keeps growing. So in this sense, we notice that the system is not stable in the bounded input, bounded output, meaning that even though it receives one bounded input, the output could be unbounded. Okay? And if you see this happen, the system is not stable. System is not stable, right? So let me just move on to the next point. So even though Fibonacci sequence is fun to study, right? It's historically important. But in principle, in DSP, we will avoid designing an LTI system that is unstable. We don't like it. We don't like our system to be unstable. Either to process your signal, right? You have a signal and somehow you want to design low pass and somehow say, sorry, the system is not stable. It's not good. Okay, so even though this is a funny example for us to study the solution to difference equations, it turns out that this kind of system is something, this design is bad. Yeah. So later, when we come back from spring break, we start designing filters, right? So one of the very basic requirement is to make sure that all our design are stable. We don't want any unstable filter, okay? So even though the sequence is fun to study, in principle, we avoid designing any system that is not BIBO stable, right? And we learned that, therefore, when given a difference equation, if you're kind of your client, right? You ask somebody to design a filter, and you pay somebody to give you a difference equation, basically. When you design a filter, you pay somebody to give you a difference equation. So once you right? Once you receive a difference equation, the first thing you should check are the roots of AZ. Is any of them outside the unit circle? That's what you should do, seriously, to ensure stability in something that you pay for. Okay? So let me read this. Therefore, when given a difference equation, which might be somebody you employed, you pay somebody to give you a difference equation in the form of equation 1, linear constant coefficient difference equation. We want to check if any of the roots, denoted as Pj, any of the roots of A of z is outside unit circle. Okay, check that. If any one of them is outside, then this difference equation has a diverging impulse response as n approaches infinity, something like that. You'll have this impulse response will have a factor, a term like that, which diverges if any of the roots is outside. Okay, then you should ask them to 砍掉重练, right? Please, you should discard that equation, right? Ask your client to spend more time and fix the problem. It's a problem, okay? In principle, we don't want the difference equation to have a causal but diverging impulse response. It is unstable. We don't like it. Right? So far, so good. Yeah. That's kind of a lesson. That's a lesson that sometimes could happen also for your research. Yeah. And the final point on this slide is a definition. It's simply a terminology. Okay? The root of AZ. So I'm making a cross. Yeah. I mark the root, the two roots with crosses. So we'll be, in the semester, we'll keep using this notation, okay? Wherever on the complex plane where AZ is 0, the roots of AZ is marked with crosses. 用打叉来标注啊。What are the crosses? And they have names. They are called the poles. They're called the poles or 极点, poles, of the system. The root of A of Z is called the poles of a system. And they're often marked with crosses on the textbook and also as well as on my notes. Right? We'll be using this post 极点. So the root to B of Z also have roots, and they are called the zeros. So just maybe I can erase this. So in general, what we have is yn equals to minus sign summation ak y previous samples. And we are making a linear combination of previous samples plus a linear combination of previous inputs, or where k runs from 0 to big N, right? Yeah. And then h of z, long story short, is bz divided by az, and both of them are polynomials of z inverse. We have b0 plus b1 z inverse plus something, please, b big N z minus n divided by 1. The leading coefficient is always 1. Plus A1 z inverse plus blah blah plus a, the last term, an z to the minus nth power. Okay, so that's our system function. And then you can factorize the denominator, okay, as basically 1 minus p1 z inverse, 1 minus p2 z inverse, and so on. And in general, it should have m roots. But on top, you can also do the same. B of z also have roots. B of z also has roots. And the roots of A of z, which are P1, P2, all the way to all these P things, are called the poles. P1, Pm are called the poles. Whereas, let me just write down the, maybe on top. On top, you can also try to factorize, that can also be done. Factorizing the B of z, you may have 1 minus Q1 z inverse times all the way to 1 minus the last root of B of z. And here, Q1 to Qn are called zeros, simply called the zeros. So these are the terminologies that we'll be using. Poles, zeros, the roots of AZ and B of z, respectively. 极点跟零点啊。Okay, yeah, so that's about stability and terminology. So we want all the poles to be inside the unit circle. Okay, so that's kind of a take-home message. Whenever you receive a linear difference equation, check whether all the poles are inside the unit circle. If they are, you are sure that the system can be implemented in a causal and stable manner. The system will be, when you implement the systems in a causal manner, the system will be stable. Okay, there's nothing to worry about that. Now here comes kind of an exercise for us to take a look together, right? All right, so now let's take a look. This is an exercise. 多选题. We have 4 statements with our conditions, to see if we grasp the ideas that we are studying right today. Suppose that we have an LTI system with impulse response, small h, and system function, big H, which is the z transform of small h. And suppose that h of z can be written as b divided by a, where both are polynomials. And also we assume that the system is causal and stable. If the system is causal and stable in the bounded input, bounded output sense. Right? So let's see which of the following statements are true. First statement, all the poles of systems are inside the unit circle. Is it true? My answer is yes. Okay? All the poles should be inside the unit circle, given that we are told the system, now after ensuring that the system is stable, all the poles are inside the unit circle. Second, the Fourier transform of Hn exists. Is it true? If all the poles are inside the unit circle, then the region of convergence includes the unit circle. The region of convergence for causal systems should be outside the largest circle, right? Outside the largest radius. But now all the poles are inside the unit circle. So the region of convergence, let me draw a picture. The second answer, my answer to the second statement is also true. If the system is stable to begin with, then all the poles, there might be, if the order of a filter is high, there might be multiple poles. But if all of them are inside the unit circle, here I'm drawing a lot of poles, but if all of them are inside the unit circle, then what is the region of convergence? Region of convergence is outside the largest radius, right? region of convergence is outside largest radius, which might be this thing right here. That's the pole that is furthest apart, furthest from the origin. This might be the pole with the largest radius. And the region of convergence will be outside this circle. Here I'm probably, which include the unit circle, right? So long story short, as a result, the region, the ROC includes the unit circle. That means the Fourier transform can be evaluated. That means that we can evaluate the transform on the unit circle, which is the Fourier transform. Okay? So there are different ways to talk about this, but yes, in this case, if the region of convergence is outside the largest radius, which turns out to include the unit circle, then, I'm just giving myself a hard time. Anyway, so then the Fourier transform of h of n exists. Okay, so my answer to the second is yes. Stable system has Fourier transform. The impulse response has a Fourier transform. Okay, and now moving on to the third point, limit. Does the impulse response approaches 0 in time when time goes to infinity? If all the poles now are inside the unit circle, if all the poles are inside the circle, can we conclude that the final value, some people say, when the final value, h of n, approaches 0 in time as n approaches infinity, can we say that? Can we be sure? and增加你点头了啊 Why? Because take a look at here. Okay, my answer is also a yes. Because if you take a look, that we know that even without knowing alpha, exact value of alpha 1 and alpha 2, but the bottom line is that if all the poles here, P1, and in this case P1, P2, and more generally it could be P1, P2, P3, and so on, but if each of them has an absolute value of less than 1, then what happens? Then when n approaches infinity, they converge. Every term converges to 0. Therefore, the sum also converges to 0. That is, say, h of n converges to 0 as n approaches infinity. Okay, that's also a property for BIBO stable system. Okay, so my answer to the third point is also a yes. 3 strikes. Okay, the last one. H of z converges over the entire complex plane except at z equals to 0. Is it true? Is it true? If h of z is defined as summation hn z minus n, does it convert over the entire complex plane except at z equals to 0? At z equals to 0, apparently it doesn't converge, right? But how about elsewhere? Okay, does it converge everywhere except at z equals to 0? And of course, the answer is no. The answer is no, because there's a region of convergence. Okay? It converges only outside the largest circle right here. Okay? Inside the largest circle, this sequence, this power series, if you will, does not converge. Okay? Yeah. So true, 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 false. Right? That's my answer. Okay? Yeah. So that's about all I want to emphasize for today. We have one final slide. Okay, we have one final slide. Any concern, any comments on here? Is something unclear? Yeah. Is everything okay right here? Yeah. It's a lot of information today. Yeah. But here's almost everything I want to say about difference equations. How do we find the solution? And once we find the solution, we found that we need to care about the roots, location of the root to A of z. Okay, so that's something I want to emphasize. We want all the roots of A of z to be inside the unit circle for a system to be stable, right? So that the solution can be written in something like this, a sum of geometric series, where the common ratios, 这些公比啊, the common ratios are the poles. Okay, so there's one last slide before we leave. This is a tricky slide. It's a tricky slide, okay? So take a look. I need some room here. So let me erase a few things. So this slide is about that when we write a difference equation, the more natural way is to let the time go forward. 时间要往前走. That's a more straightforward way to think about difference equation. But it turns out that you can also think of a difference equation by making the time to go backward. This is strange. So this is strange, okay? So, but this is one last slide I want to share with you. So the idea is go this, which is not recommended. I don't recommend doing this. I don't recommend doing this. But let's begin with still this equation, okay? Yn equals to y sum of 2 past samples plus any input that we receive. Yeah, as a one line of code or as an equation, mathematical equation. We say like any n, right? Any n being integer, right? But somehow, if this equation holds for any integer, how about we let n prime equals to what? Yeah. So n plus 2. How about, let's try this, yeah. If n prime is n plus 2, okay, so then we have y n prime. Okay, y n prime is n plus 2 is equal to, now n prime is n plus 2. So now we are using this equation by plugging and by replacing n with n plus 2. Okay, yeah. So now we have n plus 2 minus 1, that's n plus 1, plus y, n plus 2 minus 2, right? So this is strange. It's really strange. Now x of n prime is n plus 2, okay? Now we have, and the next, now let's keep yn on this side of the equation and move everything to the left. Or, yeah, let's call left, yeah, you know what I mean. Then yn equals to y n plus 2 minus 1 n plus 1 minus x n plus 2, right? This is what I said. Now the time is going backwards, sort of. Yeah. Why? So if you consider this being one line of your computer code, then what we have is that an expression of y of n in terms of its future samples. Y of n can be expressed in terms of future sample. It ought to be equal to 2 samples later minus 1 sample later minus the input that we will receive 2 samples later. So if you take a look at this, is this wrong? The question is whether or not this is mathematically incorrect. Is something wrong here? Seriously, is something wrong here? Okay. Time is up. Okay. So when we come back after spring break, let's spend some more time to think about this. Okay. This last slide will not be tested. 这个期末中考不考这个，先不要管这个最后这样啊。So the midterm will not test you on the last slide. But when we come back, let's spend more time on this slide. What's going on? Is it mathematically incorrect to say so? Yeah. Given the difference equation, given that the difference equation has to hold for all n, can we just jump a few steps and reach this conclusion that the current sample will depend on future sample? Something's wrong or nothing's wrong. Okay, so when we come back, let's bring this question back to the classroom. All right, so see you tomorrow, and we'll do a mock exam discussion. Thanks for being here. See you tomorrow.